how do you get 39?
The number added by that gets reset by 2.
So what do you mean by that?
I mean, it added from 3 to 4 added by 1, 4 to 7 added by 3, 7 to 12 added by 5.
So you kept adding by the odd numbers.
Yeah.
1, 3, 5. Now, I'm going to let you know right now, that's correct. For everything we're going to do going forward, when you see this pattern, add 1, add 3, add 5, add 7, add 9, think perfect squares. What are the perfect squares? What's 1 squared? 2 squared? 3 squared? 4 squared? 5 squared? 6 squared? 7 squared? And so forth, right? When you see this pattern, think those numbers. This is going to become important as we do more in this chapter. When you see those numbers, you think, because we're going to have to find formulas and different kind of stuff with all of this as we go forward, and it will be related to these numbers. How is that related to these numbers? It's those numbers, okay, plus what? Okay. Well, let me add one more number to this list. Now.
Oh, yeah, plus 3.
Plus 3. So it's clear with this. Didn't that help? Isn't that obvious now? It's just add 3 to each of these, right? So it is 39. Your pattern is correct. I'm not saying that it's not right.
But that's a.
It's just you want to think about it in this, because if you want to go like further ahead and you recognize that, and you can say, oh, 100 plus 3 is 103, instead of having to necessarily figure out all the ones in between by just adding on and so forth. All right, the last two. I think what's there, you mentioned the last one.
Yes.
What is it?
13.
13. And how'd you get that?
It's like you take the first 2 numbers and then add them and gets the next one. So 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals
13,
13.
which is what sequence? That's a Fibonacci sequence. Fibonacci sequence, a very famous sequence in mathematics. Fibonacci, a famous mathematician. I'll explain why here in a little bit if you haven't seen it before. We're not going to spend a lot of time here. What about number 5? No. How about I show you the answer and then you figure out the pattern?
Sure. Yep, so this is lost.
You can just set it there.
Okay, can you clear these for me?
Yep, I'll clear them again.
I got a couple more, I'll bring 4 more, bring out to you too.
Okay,
Thank you.
no problem. You get it?
No.
Okay, so let's look at what we have already. These are kind of the type of sequences we're going to look at in this chapter. There's different types here. I think these examples are very specific. To get the next term, you just add 3. To get the next term, you multiply. To get the next term, there wasn't really any mathematics that you did. It's just a pattern. To get the next term, it was based on some set of numbers, and you had to add 3 to something, or you could do adding the odds, right? But notice, here you're adding the odds. That's different than just adding the same thing every time, right? Here you had to add something different every single time. There was a pattern to it, but it wasn't the same thing. Down here, you added 2 numbers, but your next number always depended on the last 2 numbers, right? So here, when you added 11 or 9, it didn't really depend on what the last number was, right? You just added the same, you added this pattern. Here, it depends on what the last 2. This one is totally different. How do you get the next term? The 18 is my birthday, the 8th is my wife's birthday, 20 is Sarah's birthday, 29 is Luke's birthday, and 12 is Aaron's birthday.
Gosh.
This has
How am I supposed to know
absolutely
that?
nothing to do with math, like calculating at all. It's just a random sequence, not random, it's a set pattern to it, but it's got nothing to do with like mathematical quantities or calculations.
Okay, at least it does, because like, I was like, what?
And don't feel bad, I mean, Sarah didn't get that one right when she was in the class. She still didn't recognize the pattern, so you guys have no chance.
Do you know if we got it right?
What's that?
Did we get it right?
I don't know, he's in here next period, but he's quarantined, so he won't even be here, so. We can have him zoom in. So, okay. All right. So what we're looking at here are sequences. I need to open this up. So we're looking at sequences. This chapter is sequences and series, and today we specifically want to look at sequences. And a lot of this you have you've seen, I think, in Algebra 2 and Algebra 1 and some classes previously, things like arithmetic and geometric and all this other kind of stuff, and some of the notation. Those Fibonacci sequence, we're not going to do the Fibonacci sequence project. We're kind of out of time. Fibonacci sequence, I'll just give you a real quick rundown. Fibonacci sequence are these set of numbers. You add the two previous terms to get the next term. And I'll just say Fibonacci sequence is directly related to the golden rectangle or the golden ratio. And it's just this kind of mythical number that supposedly pops up everywhere in different types of things. If you go through and you look up, like this, does anybody here play the piano? By chance, anybody musical in here at all? So I'll use a different one. One area, Fibonacci sequence has a tendency to pop up in nature. In flowers, if you look at flowers, like daisies and certain flowers, not all flowers, but some, they will always have the number of petals as a Fibonacci number. You'll never find one that has 10 or 12 petals. It'll always be a Fibonacci number. If you look at sunflowers or pineapples or things, and you look at their spirals of seeds on those plants, they're always a Fibonacci number. They're never something else. And there's a whole bunch of these kind of connections in science and stuff. A whole bunch of video on YouTube, just YouTube Fibonacci sequence and stuff. Byhart has a really good one where they show all the places this is. It's connected also then to Fibonacci sequence is connected to the golden rectangle, which is something that's also connected to everything from how they built buildings in the ancient time to the size of the ark in the Bible and all kinds of stuff. It's connected to Fibonacci sequence. Good question.
I was just curious to know, like, Fibonacci spiral, is it based on that?
Yes, Fibonacci spiral. I'll go to a picture of the Fibonacci spiral. There you go. There's the Fibonacci spiral. The spirals in nature are related to the spiral. So how the Fibonacci spiral comes in is you have a golden rectangle, which is right here. And the way the golden rectangle works, I'll go back up here. The golden rectangle is this rectangle where your width and length, when you divide, you get that number, which is the golden ratio, the golden rectangle. And as you take pairs of numbers in the Fibonacci sequence and you divide them, it gets closer and closer and closer to that number. That's how it's connected. So how the Fibonacci spiral works is you take a golden rectangle, right? And then you make this right here a perfect cube. What you're left with over here is a new golden rectangle, same proportions. And then you take a cube off of that. And what you're left with is a new golden rectangle. Take a cube off of that. you're left with a new golden rectangle. Take a cube off of that, and you just keep repeating that over and over and over, smaller and smaller. You start back here, and you go through all of these cubes that you made, and you will get that spiral, which is the exact same shape of the spiral. If you look at like a nautilus or a snail or something like that, that's the shape that their spiral will be in their shell. So, some claim it's like this divine number that God has in everything that He's created, which he could have if he wanted. Some claim that there's some mathematical and scientific things you can show that if like you build it like this, or if you do the leaves and petals like this, there's some benefit to like constructing stuff, or like with the leaves of getting the most sunlight replacement of the leaves, and it's more just optimization of nature than anything else, and it just works out that way. So a lot of stuff on that, but I'm going to skip all that. All right, let's talk about sequences. Usually there's a project you guys have to do, and PowerPoint and presentations and stuff, and we're getting to the end of the semester and running out of time, so I'm just scrapping that. All right, so a sequence. A sequence is just a set of numbers called terms arranged in a particular order. It could be a very mathematical order, 1, 4, 7, 10, 13. Add 3 to get the next term. Or it could be something where there's really no math at all. 18, 8, 20, 29, and 12. It was just a random pattern, so to speak, that represents that. Okay? Let's talk some notation. We're going to say A sub 1 represents our, I miss it. Oh, here we go, sorry. I was looking at your notes. A sub 1 represents our first term. A sub 2 represents our second term. This is a notation thing, this little subscript, right? So it's a way for us to list what our terms are. A sub 3, so forth and so on, down to A sub n. That is our nth term. Okay? So if I give you an example. Okay. Is this on your notes? There we go. That's on your notes, right?
Yes.
Okay. So, by the first 4 terms, if I say A sub n is 4n minus 1, that's our formula. And I want to find what is A sub 1. That means I'm going to put 1 in for n. So this is just 4 times 1 minus 1 is 3. So our first term is 3. A sub 2 would be 4 times 2 minus 1, which is 7. You find 3 and 4. Three is 11. 4 is. So that's just using this formula to find our certain terms. Okay? Now, that formula can be in different ways depending on what type of sequence it is that we've looked at. Now, 2 we want to look at to get started here are arithmetic and geometric. That looks like arithmetic, but it's pronounced arithmetic. Why? They pronounce something different. Okay. And geometric. These are 2 types. There's a lot of different types. If you look up top, find the next term of your sequence. Number 1, 1, 4, 7, 10, 13. That's arithmetic. 3, 4, 7, 12, 19. Excuse me. 1, 3, 9, 27, 81. That's geometric. The other 4 are not arithmetic, and they're not geometric. So it is possible to be neither of these two, but these are the two basic ones that we want to look at, okay? So, arithmetic. The arithmetic sequence, the sequence where the difference of any two consecutive terms is constant. What that means, maybe a little easier, what that means is you just add the same thing to get the next term. So if we have 2, 6, 10, 14, what do you add to get the next term? 4. That's our difference. If I have 17, 12, 5, and 2, it's going to be -5. Our formulas are always based on what you add to get the next term. So yes, can you think, well, I just subtract 5 to get the next term. Does that work? Yeah, that gets you the next term, but in the formula we're going to look at here, it's always what you add to get the next term. Geometric sequences is where the ratio of two consecutive terms is always the same. This basically means you multiply to get the next term. Arithmetic, add gives you the next term. Geometric, you multiply to get the next term. So just like back here, how did we get 4? You would take 14 minus 10. 10 minus 6. You subtract the difference. For geometric, we're going to divide. 64 divide by 16. 16 divided by 4. 4 divided by 1. 4. It's got to be the same. You can't have a sequence where one time you divide by 4, the next time you divide by 3, the next time you divide by something else. It's got to be the same thing every single time. What about 81, -27, 3, -3? It's going to be -3 divide by 9. 9 divide by -27. It's going to be -1/3. And if you need to use a calculator to help you see that, you can have it was -3 divided by 9. -3 divided by 9. Nine divided by -27 to get your answer. And I show you that because when you look at the next one, 8, 12, 18, 27, kind of a hard one. So if I said, well, what type is that? First, think arithmetic. What would I add to get the next term? Add to get the next term. Okay, not arithmetic. It's not the same. What about multiply? Well, to look at that, let's go to our calculator. And as we look at that, I have 27 divided by 18. Now through the next two terms. 18 divided by 12. 12 divided by 8. So you can see what is our R. 1.5. Now, I use that example because that's a hard one to look at and just see without using the calculator, right? That's really hard to look at 8, 12, 18, and 27 and be like, oh yeah, that's 1.5, be safe. No, not really, right? That's not easy to recognize. But when you look at these and you're trying to figure these out, you're like, okay, obviously I can see you don't add the same thing each time. Let's see what happens when I divide. So actually take the numbers and take that divided by that, and that will help you see. All right, so let's determine, are these arithmetic, geometric, or neither? So as you look at this, 3, 6, 12, 24. Because I am multiplying by 2. So this we say is geometric, and here my R is 2. 2, 5, 10, 17. What do you mean by not sure? Hey, you can't just look at it. First off, so let's look at what's the addition. What are you adding each time?
3 and then 5.
So, okay, so it's not arithmetic, so we're good. Now let's figure out what about divide and see what we get. If I take 17 divided by 10, I don't know, I get something. What's 10 divided by 5? So I don't get the same thing both times, so that means it's not geometric. So it's neither. Yep, neither or neither. It's auto. Tomato. Okay, caramel, caramel. And actually, what's the pattern? 3, 5, 7. It's related to the perfect squares. 1, 4, 9, 16. It's actually related to the perfect squares. And then what about 3? 7, 1, negative 5, negative 11. Arithmetic?
Same thing. Okay.
And what's the difference? So let's say we're looking at a sequence. And even if we look at a simple one like number 3, I say, what's the next term? Negative 17, right? You just subtract 6. What if I said, what's the 100th? You're going to have to like go through and subtract 6, subtract 6, subtract 6, subtract 6, subtract 6, subtract 6, and keep track of all that. Or you got a formula, and that's what we're going to look at next. Yep, geometry, or might even be algebra 2. Maybe even algebra 1. Okay. So, and actually, this one, the geometric one, should look familiar. You guys did it with Patrick.
Yeah.
Remember we were doing exponential functions, and he talked about the geometric, and I skipped over all that because I knew we're going to come back to it here and just kind of look at all these together and look at the different types. So, let's look at our 2 formulas here. So, for arithmetic, if we want to find our nth term, we just plug in a formula, a sub 1, n, and d. If we want geometric, we plug in our formula, a sub 1, r, and n. This is why it's important, your d is always what you add. If you think subtract 5 and you think d is 5, it's going to mess with the formula. It's always what you add to get the difference. So, let's look at an example. Find the 20th term of 3, 6, 15, 21. Step 1, you got to figure out what type is it. It's arithmetic because you add 6. So that means that's my D. So if I want to find my 20th term, it is my first term, 3, 20 minus 1 times 6. We type that in the calculator, 97. You think that's right? I think that's wrong.
Oh my god.
Hey, I'm wrong.
I got 117.
That's what I got.
Got point 20. You're close.
And potato rock.
My number.
What about 3, 9, 27, 81? Geometric, so we're going to find out. One of the things with geometric, going back to when you did exponentials, what do I multiply by here, by the way? 3. Is these get really big, really fast. Okay, so let me put it in the calculator. This is going to be 3 to the 19.
Holy
Wow.
So they get really big, really fast with exponentials, just so we understand that. Okay.
Scientific limitation.
So there's a number right there. Okay. Just because you're rating things as exponents, exponential.
So on the wizard test, if number like is that big, you want us to write down that whole thing?
Yeah, you can just write down, just put it in the calculator. It's not gonna be so big, it's gonna like blow up your calculator and overflow or something like that. Okay. The other problem is, if it's exponential, like with exponential decay, it could get really, really small and give you answers in scientific notation, which, 0.00000000 or something like that. Okay. Now, so this is, we're gonna find a certain term. Let's do one more thing here today. Not homework yet. Find the formula for the nth term. This is almost the same thing. But I want to find the formula for the nth term. Now, we use the same formula. So what's my first term? 3 plus n minus 1 times 6. So now, I'm finding the nth term. If I wanted to find the 20th term, I plug in 20. If I want to find the 100th term, I plug in 100. For the second one, same thing. A sub n is 3 times 3. And now we just have a formula for that term instead of. So we're using that same formula. So if a sequence is arithmetic or geometric, there is your formula. Piece of cake. What if it's not arithmetic and geometric?
Wing it.
How do we find the formula? These are the fun ones. We're not there yet. No. Basically what this does is, we're going to look at some tricks you can use, but basically, can your brain come up with the pattern? So, let's think about this. First thing I'm going to ask you to do, the first step I would say to help you figure this out, is determine what is the next term. Can you figure out the pattern to find the next term? So, what is the next term?
26.
26, and then 37, okay? Those are the next two terms, right? So first, can you kind of recognize the pattern?
Yeah.
Next, what about this? This is when n equals 1, 2, 3, 4, 5, 6. The next term is going to be 7. Can I figure out how to find the next term based on 7? What is the next term? It's 50. So can we start to figure out what the pattern is? What's the pattern?
You go back, you go every odd numbers, so the first one, you added 3, the second one, 5,
So here's the question, right? What's our formula? If I say, let me get rid of 7 here for a second, and I say, keep going, keep going, keep going, and I get to the nth term, what is that pattern?
you know?
No, I know.
Okay,
Used.
if I say again what you said earlier.
So, you add the odd numbers up, so you go up line, so the first one's 3, the third one's 5, added 5, and 7, and 9, 11, 13, 15.
I've already told you the answer already today.
Square plus 1.
It's perfect squares.
Oh, crap.
What's 1 squared?
1,
What's 2 squared? 3 squared? 4 squared?
16.
5 squared?
30.
So for the n term, it's going to be n squared plus 1. And when you see that pattern, that's why I said that way back at the beginning. When you see that pattern, plus 3, plus 5, plus 7, plus 9, plus 11. Ding, 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 bells and whistles go off in your head, perfect squares. It's based on the n squared, okay? That's why you said that at the beginning, okay? What about the next one? First step, think about what are the next two terms? Five over 36. 6 over 49. And then looking at the pattern, this is my first, second, third, fourth, fifth, sixth. If I'm looking for the n, what's going to be the pattern here? Now, this is not arithmetic or geometric. This is not, no, here's a formula, plug it in. This is your brain smart enough to figure out the pattern and find the formula? Frankly, no, it's not. I'll just say that now.
Well,
The top's easy. What's the top?
And add one.
No, for the nth term. Just n. And what's going to be on the bottom?
N plus one squared.
N plus 1, whole thing squared. So my nth term, n plus 1. All right. I'm going to give you the homework. If you do the first 11, this is like 2-day, or we're going to continue this tomorrow, and then tomorrow we'll do the back. Tomorrow.
okay.